Good day, everyone. For this particular video, we'll continue with the origin of heavier elements in the universe. So the density inside the star is great enough to sustain fusion for extended time periods required to synthesize heavy elements other than beryllium, lithium, helium, and hydrogen we've learned earlier. So the process where heavy air elements are formed is what you call as a stellar nucleosynthesis, the formation of heavy elements by fusion of lighter nuclei in the interior of stars. Take note, there is a fusion of lighter nuclei in the interior of stars. This happens in stars. There are many nuclear synthetic pathways or nuclear fusions to produce heavy elements. We have the three proton-proton fusion, carbon-nitrogen-oxygen cycle, and the triple alpha process. So we'll discuss each in the later slides. So first, hydrogen fusion by the proton-proton chain. So step one here, two protons fuse to make a deuterium nucleus, one proton and one neutron. This step occurs twice in the overall reaction. So we have here two protons, fuse together to form one proton and one neutron, which is a hydrogen, a specific type of isotope of hydrogen called as deuterium. Now, step two, the deuterium nucleus and proton fuse to make a nucleus of helium-3, two protons and one neutron. So we have here a gamma ray being excreted in this particular process, where there is formation of two protons. This signifies that this is already helium because we already have two protons here and one neutron. So this is helium-3. Again, this is a helium because we have two protons in this particular atom. Two protons and one neutron, making it helium-3, releasing gamma radiation in the process. And step 3, two helium-3 nuclei fuse to form helium-4 with two protons and two neutrons, releasing two excess protons in the process. So we have here a proton decay, or proton is being emitted in this particular process. And we have here the fusion of two protons and two neutrons. We call this as a helium since we have two protons here, helium-4, a specific isotope of helium. Next process is the CNO cycle, or the carbon-nitrogen-oxygen cycle. This is a set of fusion reactions that occur in stars to convert hydrogen into helium. So we convert here hydrogen into helium with catalysts being the carbon, the nitrogen, and the oxygen in the process. So what is happening here is it is a catalytic cycle, meaning that unlike the proton-proton reaction, which consumes all of its constituents, the CNO cycle is a repeating cycle that uses carbon, nitrogen, and oxygen isotopes as catalyst. Double catalysts, they are actually not being consumed in the process, but it actually speeds up the operation. So each of which is consumed at one step of the CNO cycle, but regenerated in a later step. Because when we talk about catalysts, they are not um, they are not being lost in the process. They are not consumed in the process, but they are just being used to speed up the reaction. So we have here again for the Skinner cycle, the carbon, the nitrogen, and at the same time, the oxygen as our catalyst in the operation, producing um, converting hydrogen into helium in this particular operation. And the last process is the triple alpha process. The triple alpha process is a set of nuclear fusion reactions by which three helium-4 nuclei, or the alpha particles, are transformed into carbon. Take note, when you encounter the word alpha particle or alpha radiation, the main the main character there is helium with 4 as the mass number because it has two protons and two neutrons in its nucleus. So this is what you call as the alpha particle. So origin of heavy elements. Layers near core of stars have very high temperatures enough to nucleosynthesize heavy elements such as silicon and iron. Do you think elements heavier than iron can be formed through fusion? The answer here is it cannot be because i- it is formed through fusion as tremendous amounts of energy are needed for the reaction to occur. So fusion is not enough to produce heavy elements other than iron. So the what is the operation to produce heavier elements other than iron or heavier than iron? So we have here what you call as a supernova. Heavy elements are formed in a supernova, a massive explosion of a star. So this is a supernova where it is an explosive death of a star. It is where other elements heavier than iron in the periodic table are formed through explosion of a star in the universe. So we have here the neutron capture reaction. In a neutron capture reaction, heavy elements are created by addition of more neutrons to existing nuclei instead of fusion of light nuclei. So there is no longer fusion here, but an addition of neutrons to a nuclei to produce heavier elements other than iron in the periodic table. So this is the diagram. Beta particle are being produced here, but neutron is also being captured in the process. So the concept of atomic number that led to the synthesis of new elements in the laboratory. So we have here the anatomy of a nuclide. So this is an element, number 8 in the periodic table, with 8 protons. You call it as oxygen. In here, this is just an isotope of oxygen because it has 17 as its mass number. So meaning it has 8 protons in the nucleus and 9 neutrons in the nucleus. That's why it's making it as 17 as our mass number for oxygen. This is just a specific isotope of oxygen. So again, we have here oxygen, that is number 8 in the periodic table, and thus it has 8 protons. And here, at the same time, we can see the mass number, 17 is the mass number. This means that in the nucleus of this particular oxygen isotope, there is 8 protons and 9 neutrons, making it 17 as the mass number. So this is a nuclear equation that we need to examine for you to familiarize as well. So in here, we have uh, an alpha radiation happening here since we have here 2, which represents helium, with 4 as a mass number. That means 2 protons and 2 neutrons. Combine it with nitrogen, that's number 7 in the periodic table, 7 protons, and a mass number of 14. That means 7 protons and 7 neutrons in the nucleus. Add them together, that's 14 plus 4. The other side or the product side must also contain 18 as the mass number in total. And for the proton at the bottom or the atomic number, it must have 9 as the total as well to make it balanced. So here the product is oxygen, number 8 in the periodic table with 17 as the mass number. And we have here an emission of a hydrogen atom, a proton in this particular process where there is one proton and at the same time there is no neutron in this particular case. So again, the left-hand side of this particular reaction is a reactant, meaning these are the materials that react in a process during this nuclear equation or radiation, and the right-hand side is what you call as the products of this particular process. These are being produced in the process. We have here oxygen and hydrogen. So, nuclear transmutation. So, another one that we need to examine is in this particular illustration. So we have here beryllium, number 4 in the periodic table, having 4 protons, and we have a mass number of 9. That means there is 4 protons and 5 neutrons in the process, or inside the nucleus of your beryllium. Add it with an alpha particle or the helium particle having 2 protons number 2 in the periodic table, and 4 as the mass number. That means there are two neutrons and two protons in the nucleus of your helium. Add them together, 9 plus 4, that must be 13, and 4 plus 2 at the bottom must be 6. So this is the reactant side, and it must be balanced with the product side. So as you can see here, upon checking in the product side, so we have carbon, number 6 in the periodic table. So we already have 4 plus 2, 6. That's equal already. And also, for the mass number, 9 plus 4, that's 13 minus 12 for the carbon. So there is lacking 1. And that means that there is an emission of a neutron in this particular case, wherein neutron has zero atomic number. It has no charge. That's neutral. That's zero. And it has a mass, by the way. So it has 1. So 12 plus 1, that is 13, that is equal to the left-hand side of this particular equation. And 6 plus 0 is 6. And on the other left side of this particular transmutation, nuclear equation, is also 6. That means this equation is already balanced. So just a little trivia. Now, when talk about transmutation in the nuclear radiation, technetium is the first artificial element now formed in this particular case. So that's it. That's the idea where heavier elements were formed in the periodic table. So we have the stellar nucleosynthesis, and at the same time, we've learned that heavier elements other than iron in the periodic table were formed using a supernova or the death of a star in a particular process.